So this is a classic, or one of many kinds of classics, right? But this sort of shadow problem. A man is walking towards a lamppost, away from a lamppost, towards a spotlight, whatever, something like that. These kinds of problems are very standard related rates problems, and they're pretty, you have to pay attention to what is what, but they tend to be basically a similar triangles setup. So there's triangles involved, but rather than being Pythagorean theorem, it's similar triangles. So what you'll see if you look at this problem, in this case, the spotlight's on the ground, shining on a wall. The wall is 12 meters away. A man 2 meters tall walks toward the wall from the spotlight, and they tell you how fast he goes, right? So the question is, how fast is the length of his shadow on the building decreasing when he is 4 meters from the building? So let's draw a picture here. And so here's my spotlight. Here's 12 meters. Here's my wall. And here's my man. Okay? So what's going to happen is, what's going to cast the shadow is just go from the top of his head, right? So the wall goes up there, but we don't need that part. This is going to be the length of his shadow on the wall. So let's call that y. Okay? And this man is 2 meters tall. Okay? And his height isn't changing. He's always 2 meters tall. This 12 meters, which I'm going to put down here, is this whole distance. Right? The distance from the light to the wall, that's not changing. But he's walking, right? So the distance, and it doesn't, I'm going to call this distance x, right? This is the distance he's walking from the spotlight to the wall. And walks toward the wall from the spotlight at a rate of 1.6 meters per second. So that's telling me that I want this distance to be x, right? The distance from the man to the spotlight, right? Because that's what they're telling you, that this is increasing at a rate of 1.6 meters per second, okay? So what we have is, what they tell us that dx dt is 1.6 meters per second. Positive, right? Because he's walking towards the wall, so this distance is increasing. And what they want is, they want to find the rate at which the shadow is decreasing, right? So find dy dt. And by the way, you'll notice they tell you the length of his shadow is decreasing, so we would actually expect the answer to be negative if we set it up right. So that's kind of a good thing to know, keep in the back of your mind. Okay, find dy dt. Okay, when? Well, now we have to worry about some of these things, okay? So first of all, we'll worry about that in a minute. How do I use these similar triangles? Well, you can see where the triangles are. You've got the small triangle here and the big triangle there. So however you want, the ratios are the same, right? So x is to 2 as 12 is to y, or x is to 12 as 2 is to y, however you want to set up whichever ratios. As long as you do corresponding sides in the right way, you'll get the right thing. So if I work this out, what I have is xy equals 24. Right? Okay, so that's my relationship between x and y. All right, now, I'm going to take the derivative. Notice I've got x times y. Both x and y are changing with respect to t. As he walks, x is changing, and the length of his shadow is changing. So, but now when they're multiplied by each other, so this is a product rule one. So you have to think about them in this way. You know that this is the product rule of two functions of t. So when I take the time derivative, of this whole thing, I get x dy dt plus y dx dt, and the time derivative of 24 is just 0. Okay, so that gives me dy dt equals minus y over x dx dt. Now I can plug in my stuff, but I have to be a little bit careful here when I read the problem, because they tell me 4 meters, but we don't want to plug in 4 meters for x. So what is the 4 meters? Because it's telling me he is 4 meters from the building. So this is telling me that at the instant that I'm interested in, this distance here is 4. Right? Not the distance x, because x is the distance from the man to the spotlight. So that's why I'm saying they can switch this around and do stuff like that. You have to read them carefully. Okay? So, but where I read it carefully, it says he is 4 meters from the building. That means when this is 4, the x is 8. So x equals 8. Okay. When we care, so at the instant, x equals 8. Now what do I do? How do I find y? I could go back to my original, either this one or this one, right? X times y is 24. So y is 24 over x. So 24 over 8 gives me 3. And now I'm set. I just plug this in here. So I've got y, which is 3, x, which is 8, and dx dt, which is 1.6. Okay, and this can be meters per second. So what the heck is this? Minus 3 and 8, that doesn't even look like an 8, and 16 over 10. So this is a 2, so minus 6/10 or 3/5 meters per second, or 0.6, right? Whichever way you want to write it, I don't care. Sorry, that's very small, but what we do get, I'm going to put it in a box here so we can see it. Okay, and now I did want to point out, we can see that the answer is negative. So that makes sense with what we were saying before, that the shadow is decreasing. If you messed up, I actually did mess up, and I got a positive answer. I knew that that didn't make sense because I had to have the shadow decreasing, so that told me my answer isn't right. I had to go back and figure out where I messed it up. Okay? So the first time I did this problem, I did mess it up, but I knew it because I was paying attention to what it was telling me and what the sign of my answer was, making sure that my answer makes sense.